Yes. And you can just call me Karim. You don't need to call me Professor or anything. As hard as it might be. Try it the next time. I know. Yeah, I know. Yeah, I know. I still call my professors from my undergrad doctor or professor. I just can't get myself to call them by first name basis on first name basis. Yeah. Hi Evan, how's it going? I hope you can all see my iPad screen now on the Zoom channel. Sorry, on the Zoom thingy meeting. Okay, cool. All right, so everything should be all set for the Twitch live stream. The Zoom thing is working now. So hopefully my computer won't crash from all that streaming and recording and zooming and whatnot. We'll see. I'll try it out today and see how it goes. So welcome back everyone. I hope you had a nice weekend. I hope you came back refreshed, and I hope you're gonna have a nice week this week. So in today, before I start today's lecture, a couple of things. I noticed that on the e-class page, just let me check it out again quickly. Just reminding you that today at 5 p.m. you should be submitting your partner's name for the course project. So please do figure that out soon. I see a few people already making use of the e-class forum to reach out to potential partners, which is great. You can use the forum, you can use any other channels of communication that you might find more convenient for you. But please don't forget to do that. Otherwise, you might be just randomly appointed a partner. So if you really want to work with someone, go for it. Otherwise, it will be randomly assigned, basically. The other thing, so today, do grad students need a course, project, paper, presentation partner? Good question. I need to go back to the course outline to answer that question. So I believe for the course project, no. Grads will do it individually. For the seminars, yes. So if you are a grad student, you basically don't need to do anything for the course project. You're just going to do it on your own. If you are an undergrad, you need to figure out another undergrad that you want to partner up with. And I didn't put any limit or restriction on how big of a group it might be. I personally think 2 to 3 people in the group is good. More than that just becomes a hassle of managing too many people in the group. Fewer than that, it might be a bit too much work for one student given your course load. For the seminars, it's going to be groups for everyone. So for the next deadline, which is I think assignment 0.1 or something, I believe that's going to be due a week or two after assignment 0.0. So it's going to be due October 6th, so Tuesday next week. Make sure that you also select a partner, whether you're a grad or undergrad, make sure that you select a partner for the paper seminars. That's it for the announcements. Any questions or comments so far about either the assignments or the papers, seminars, course projects, or the course so far? All right. Looks like we are all good here. All right then. So in today's lecture, we're going to discuss pointer analysis. But let me refresh your mind very briefly about what we discussed last week. So we discussed very extensively what a call graph is. It's basically a data structure that represents the calling relationships between methods in a program at compile time. We need the call graph to be sound, meaning that it should not miss any edges that may happen or any calls that may happen at runtime. So it should exhibit all those potential calls that may happen at runtime. It should be precise. We should aim for the call graph to be as precise as possible, meaning it shouldn't have too many false positives, and this comes in, it's a crucial point when it comes to dynamic dispatch or virtual method calls, like in a language, an object-oriented language like Java or Scala, or any other language where dynamic dispatch and virtual dispatch is an issue. We have seen also towards the end of the lecture, I think on Tuesday, no, at the beginning of the lecture on Thursday, we've seen on-the-fly call graph construction and how practical algorithms for call graph construction actually operate. So you don't actually, you sort of compute a whole bunch of relationships together, and each one of them feeds into the other. So you find what are the reachable methods. The more reachable methods you find, the more allocation sites and call sites you find, and the more of those you find, the better information you have about points to analyses and the points to sets for variables. And the more information you find about points to sets, the better method resolution you can resolve, the better your method resolution is, and the better your method resolution, meaning you're going to get more precise information about the call graph, which will feed back again into computing more reachable methods, and so on and so forth, until the work list algorithm terminates its computation. We have seen also propagation-based call graph, Spark, in Soot, and this is a typical style of an Anderson-style analysis. An Anderson-style analysis is an analysis where the relationships or the constraints that are induced by the edges in the pointer assignment graph are subset relationships. So you sort of accumulate as you go the information that you find, the new information that you find on top of the old information that you have already computed. So you don't forget anything that happened in the past. So this is one style of analysis, of pointer analysis, that you will see also in the literature. We have also talked about rapid type analysis, RTA, single points to set of the program. So this is another way of thinking about it. Rather than having a points to set for every single variable in the program, you basically have one large points to set for the whole program, and all the objects are there, basically. Variable type analysis, or VTA, we've said that it's field-based. Main thing is that we need to simplify the strongly connected components in the pointer assignment graph, and there is no on-the-fly call graph construction in this case. So you cannot compute all the relationships all together using that work list algorithm. As opposed to the Anderson-style analysis, where the constraints of the points to sets induce subset constraints, Stensgaard-style analysis is another approach where those constraints induce equality-based constraints. So rather than accumulating old information, new information on top of the old information, you're just going to basically merge the information and assign it to both sides of the equality. So in other words, you're going to be a lot more imprecise, but it's going to be a bit faster for the analysis to compute, because there will be less intermediate computations that the analysis needs to make. And this kind of analysis sometimes is actually the better way to go in case you want to scale up your analysis to larger programs, or to certain language features like JavaScript, for example, where you can basically remove and add any kind of field to an object as you go. You can do the same thing for methods. You can redefine methods as you go dynamically. So these kind of analyses, the Stensgaard style analysis, would be more appropriate in this case than a more precise Anderson style analysis. So today we're going to basically see other variants of points to analyses, as opposed to the couple of ones that we have seen in the previous 2 lectures or so. So we're going to see points to analysis. We're going to also see alias analysis, and we're going to discuss together in today's lecture when to use which type of analysis. When does each one benefit us the most? So first we're going to start with points to analysis. So points to analysis is basically as follows. You have a variable v, and that variable v, you want to figure out what would be the possible objects or allocations in memory that this variable v may point to at any point in the program. So you want to know O1, O2, any other potential objects that variable v may point to in the program. Alias analysis, on the other hand, computes a different relationship. So alias analysis is analysis where, given two variables, v1 and v2, it will tell you whether both of them point to the same objects in memory or not, meaning the alias or not. Can you basically, for any use of A1, can you just put A2 instead? So does A1 and A2 point to the same allocation site in memory or not? I don't necessarily need to know what the allocation sites are. I don't necessarily need to know the points to sets are for V1 and V2, but I can still answer the question whether they point to the same allocations in memory or not. So it's a true-false question, basically, that you can answer with an alias analysis, as opposed to a concrete answer that tells you what exactly the objects that each variable points to. But that's not quite actually the case. So I lied a little bit there. You're gonna see now why this was not the complete picture specifically regarding alias analysis. So why is that? So let's see. So points to versus alias. So if I say I want to compute the points to a variable v, this is going to be a set of objects a1 and a2. These are going to be allocation sites, and that relationship is going to be either a may relationship or a must relationship. And we're going to get into more details later in a couple of minutes. What does it mean, may or versus must? May alias, on one hand, like each one of them, the may alias of v1 and v2 or the must alias of v1 and v2, the answer to that question is true or false. May would mean that at any given point in the program, v1 and v2 may point to the same allocation site or not. So it is enough to show or to prove that for one location in the program, and by location I mean a statement, and if that's the case, then the result of this analysis is going to be true. However, for the must alias relationship v1 and v2, if it's going to be true, so if the analysis returns true, that means that it is true for every single statement in the program. So you can think of it as follows. The may alias is basically there exists one case where v1 and v2 point to the same allocation site, and by one case here I mean statement, and if that's the case, that's enough. For the must alias analysis, it means for all statements v1 and v2 point to the same allocation sites. Sounds good? Any questions so far? Thumbs up for no questions, just to make sure that everything is going fine. Cool. Keep them coming. Don't be shy. All right. I see people now are probably copy pasting the thumbs up icon thing. Cool, thanks. All right, so now we know the difference between may and must. So let's actually have an example here. So in this example, I'm just showing a piece of code on the left-hand side, constructing an object of type A. Then we have an if condition, and if that condition is true, we're going to assign A to B. Outside the if condition, meaning otherwise, we're going to assign a new object C, to the variable C, and then we're going to assign C to D, right? And we're going to have a few questions, and I would like you to think about each one of those questions and try to answer it. You're welcome to ask me questions as well if you want to clarify anything, and we're going to do that on the Zoom chat. So the first question is, may alias A and B, is that true or false? I'll give you a minute to think about that. Oh, we have a few trues there. True. Why is that the case? Why is it true? If you're going to say true or false, 3-line. 1, 2, 3. Yes, because there exists, like right? We only need to show one path in the program where this exists for. So there exists a path in the program, meaning if we are going to take that if path, so there exists a path where A and B point or may point to the same allocation site. So in that case, may alias A and B is true. So far so good. What about must alias AB? Is that true or false? False, false, false. All right, 3 falses. Why is that? Okay, false since we may not enter the if. Perfect. Because we have a path where A and B may alias, but there also exists a path where we are not going to take the if condition, but rather we're going to skip it because the if condition is going to be evaluated to false. So we're going to go straight to the C equals new C. So there exists a path where both do not alias each other. So must alias is false. So must alias AB is false, right? What about may alias A and C? Is that going to be true? False. Why is that? Two falses. Why is that? Why is may alias A and C false? Exactly. There is no such a path where A and C are assigned to each other, whether directly or indirectly. So we cannot deduce that kind of relationship between them whatsoever. So we cannot, from an alias analysis, figure out whether A and C may alias to each other. So this is going to be false. What about must alias C and D? Is that true or false? True. D equals C is always the case, right? True, since there is no path where we don't hit D equals C, right? True, right? Yeah. That's exactly correct. So no matter whether you take the if condition, the if branch, or skip the if branch, you're always going to hit the statement D equals C. So you're always going to execute that, and we're always going to have a must alias relationship between C and D. So a must alias is typically, as you have seen, is sort of related to the control flow of the program. So we have to go back again now to the control flow graph, figuring out whether there is a node in the control flow graph where any flow in the program must pass through it. At that point, if I have a fact that is true, then it's going to be a must fact. It exists because all the paths pass through that node in the graph, which is going to make this fact a must fact, whether it's a must alias or a must any other kind of fact that we're looking for. So always remember that if you're going to compute a must alias relationship or a must dash whatever fact relationship, it is always going to have to do with the control flow of the program. So you're always going to need some information about the control flow graph to be able to answer that question properly. All right, so must alias basically needs some information about the flow, and we're going to see now why that is the case. So in this example, we have a bunch of assignments from null, so we're assigning the null value to some variables. We have the same if condition. I just added labels to some of those statements here, S1, S2, and S3, and we're going to ask a few questions here. So the first question is the following: must alias. Now we're saying that we can no longer have the query of a must alias query to just be generic. It has to be associated with a control flow, meaning in this case I'm saying A at A at S1, basically that's this case here, and this one here says D at S2. So if you're gonna query the analysis for a must alias relationship, you have to specify the statement that you're querying that variable at. So here in this statement, I'm saying does the variable a at statement S1, meaning the variable a at this statement, does it alias with the variable d at S2? So basically here, the variable d here at S2. Is that the case or not? So think about it for a second here. Do you think that a must alias at S1 must alias with d at S2? What do you think? Or maybe the question wasn't clear enough. Okay, so we do have a first answer here, a second answer there. False, there are no statements between S1 and S2 where one is assigned to other. Yep, that's absolutely right. False, there are no ADAs at S1 and S2. Exactly. So I'm bound to the locations at which I'm querying the analysis for. So we have a third one, false, D is equal null, A is equal something that is not null. So in general, at statement means immediately before or immediately after. Generally speaking, again, this is one of those things that the analysis engineer has to define. Usually, it would say either right after executing the statement or right before executing the statement. So in this case, let's assume that we mean right after executing the statement. So DA as S1 means right after executing statement S1. D at S2 means right after executing the statement at S2. But that is not always the case. So whenever you have some assumptions like that about the analysis, you need to make sure that this is indeed the assumption that is made in the analysis that you're using, so that you don't have assumptions that contradict what actually the analysis is actually doing in its algorithm. So in this case here is going to be false, just like all of you folks here said. There is no, between S1 and S2, there is nothing really that says that A and D were going to point to the same thing. Either D points to null and A points to the object new A, so nothing really changes. What about must alias A and S1, D and S3? Is that going to be true or false? True. It's going to be true. Okay. Why? True again. Why is that? True. A at S1 hasn't changed. Yes, that's right. And D at S3 is set to A. Exactly. After S3, D is equal to A unconditionally. Exactly. So here we're going to have must alias is going to be true. Cool. So let's have another question. What about must alias B after S2 and C after S2? Is that going to be true or false? False, because B is equal to null and C is not equal to null. That's right. So at this point here in the program, so this is basically where we were asking our question. B is not always null. But even if that's the case, but definitely not C. Exactly. See, that's exactly the point. So you don't need to know exactly what B points to, but even if B is pointing to A, which is new A, that is not what C is going to point to after that statement. So still, this is going to be false. Because at that point, B at S2, right after S2, is going to be null. C, or it might actually be the value A, but C right after S2 is going to be new C. So it doesn't matter what it is going to be false. What about this statement here? Or this query, sorry. Must alias B at S2 and C at S3. Is that going to be true or false? False. Why? Two falses. Why is that? C at S3 is equal to C at S2. Yes. Then same reasoning as before. Right? Exactly. Is that clear to everyone? So even though the assignment statement B equals C is there, we still cannot say this is a must alias. This must alias relationship is true, because there exists a point in the program where B at S2, right at this point, so before executing the statement, is not the same as C after S3, right after executing the statement. So this is going to be false, but if I said something like must alias B, let's say S3, and C S3, what is that? Is that true or false? True, right? Because now my must alias query is querying the value of B at S3 right after the statement and C at S3 right after the statement, and at that point in the program I have already executed B is equal to C, so I can say that yes, this is going to be true. So moral of the story is, for a must alias relationship you need to figure out the control flow of the program. Without the control flow of the program and without having an exact point in the program where you're querying your analysis for, you're not going to be able to answer that question properly. So no control flow, you cannot assume any kind of must relationship in there. Is that clear to everyone? All good so far? So if the line between S2 and S3, okay, so then we have a question here saying, what if this statement was C is equal to B, right? Would must alias BS2 CS3 be true? Okay, must alias B at S2, right? So B after this statement, what is B after statement S2? So B could be either null or could be new A, right? And what is C after? Okay, I see your point now. C after S3 is B, so that's going to be null or new A. Yes, this is going to be true. So this statement is going to be true. If that assignment was the other way around, this is going to be true. Again, like here we're assuming an Anderson style analysis where basically the right hand side of the analysis, the right hand side of the assignment flows to the left hand side of the assignment. We do not make both of them equal to each other. It's not a Stensgaard analysis. So this is one of the differences between them. If you're doing a Stensgaard analysis, it wouldn't matter which side of the equality or the assignment B or C is. Both sides are going to be equal after that statement, according to the analysis. But since we're doing an Anderson style analysis, then it is different if you have B equals C or C equals B. So if it is C equals B, then this statement here is going to be true. instead of the current false statement. Does that make sense? Does that answer your question, Robert? All right, cool. So, in general, we don't actually keep writing down all those statements and so on. So we just say must alias A and B, or must alias A and D, or must alias A and C. So in other words, if we remove all those locations, all those statements, and we're gonna see here, for example, that we have must alias AD and must alias AD, one is false and one is true. So that means that must alias AD must be false, because we have to be conservative. If you're basically ANDing, or you have a conjunction of all those must alias queries for those two variables. Must alias B and C, must alias B and C is false, so must alias B and C is always going to be false. In other words. So we have to be conservative, and since we're going to have to be conservative, then we're going to say that both must alias AD and must alias BC is going to be false for this specific example here. So, rule of thumb for must alias analysis is that if you have any kind of analysis that is a must X analysis, it has to be flow sensitive. It has to go through the correct order of the statements in the program as the source code dictates. You cannot just treat the list of statements in the program as a set of statements and you can start anywhere you want. You have to go through the control flow graph basically of the program and figure out exactly whether your statement is invalid at any point along this control flow path or not. May alias analysis or May X analysis, they could be flow sensitive, but they could also be flow insensitive, because you only need one path or one statement where that fact is true for your statement to be valid. You don't need to prove it for every single statement. So a rule of thumb, must X analysis should be flow sensitive. May X analysis could be flow sensitive, but could also be flow insensitive. Any questions so far? Yeah. If they always point to null, should we what? Sorry again? Yeah. Aliasing or not? So again, this is one of the things that the analysis engineer can decide. But I'm actually going to get into that in, let's see, where is it? I think this is gonna happen in maybe 4 or 5 slides. So you're a few slides ahead of me. But this is one of the things you can decide on yourself, like whether you want your analysis to treat null values or null references as actual references that you care about. It depends on the context. It depends what you're going to use this analysis for. For many analyses, if the variables are null, you just consider them to have no values, right? So you're not going to consider them to be aliases. But it could be the case that in some cases, you want to make this fact that yes, if they both point to null, they could alias. So it depends. The answer basically depends. I hope that answers your question, Mohammed. All right, cool. All right, so now we have seen a few examples of points to sets and points to analyses from the previous lecture and today's lecture, and we've seen alias analysis. So there is some kind of relationship between them. You can sort of tell that, well, to figure out what aliases are, maybe we can figure out something about what each one points to and then do something with that information so that we can actually get from one kind of analysis to the other kind of analysis. So let's see how we can do that. Generally speaking, if you do have points to information, if you had a pointer analysis running and you have the results, you can say that alias, the result of the alias query v1 and v2 is exactly saying get the points to set of v1, get the points to set of v2, find their intersection, if that is non-empty, then these two variables alias. Because that means that they share some allocation object or allocation site that they both point to at the same time. I have to say that this is going to be a may alias relationship, not a must alias relationship, because you're saying that this is going to be non-empty. If you want to have it as a must alias relationship, then this is going to be that their points to sets are identical, basically, and have size 1. So basically each one of them point to only one object and both points to sets are equal. So this is one way where you can go from points to sets to alias analyses. So when do we then need to use alias analysis for? If we already have points to sets, like why do we even need alias analysis? We can just go from one to the other. So let's have an example here. So in this example, we have a Java method called readProp, takes two variables as parameters, string ID and string D. And string S says properties.read, so it's reading some properties, and if S is not equal, if S is null, then it assigns it the default value D. Otherwise, it will return S. So this is a very simple read property method. Given some default value, we'll try to read it from the properties file. If it can't read it there, then it will give you return back a default value. The key point here is assume that this read statement, properties.read ID, is something that you cannot analyze. Maybe it's in some library that you don't have access to. Maybe it is some native method written in C++ that your Java analysis isn't aware of. Maybe it is some code that is no longer accessible. There could be a lot of reasons why you cannot access it anymore or you cannot analyze it anymore. But assume that's the case. Then you can say that may alias S or S and D is true, right? This is going to be true because you have a statement, you have a path, this path, if you take this if path, where S is equal to D, so that's why this is going to be true. However, you can compute the points to set of S is going to be empty set, right? Because I can either say, well, this is going to be part of a library that I can't analyze, so I'm just going to say, well, it's going to be empty. I don't know what it's doing, so I'm just going to go one extreme and say it's going to be empty. Or I'm going to go to the other extreme and say it's going to be any object. Remember that diagram that we've drawn for the ideal call graph to compute? You can sort of reimagine that diagram for your ideal computation of a points to set. You cannot compute it, so you're going to get an over approximation. You can either be unsound or incomplete because you're missing some allocation sites, like in this case, that could potentially happen at runtime. You can also be highly conservative because you're going to say, well, my points to set can be any object whatsoever. So this is not precise, but sound. So two extremes of the same equation here. In either of them, it is not the accurate or the most accurate result that we can compute. So in the first case, the empty set is going to be unsound. In the second case, it's going to be an imprecise relationship or an imprecise computation. In both of them, we can't really use the relationship points to, we can go from a points to set to a may alias, right? Because if we define that may alias is, if we try to define the may alias relationship as the points to set of S intersect points to set of D is not empty, well, I don't even know what the points to set of S is, right? I can't compute it because I can't analyze that library call. The points to set of D, well, I also don't know what that is because it's some argument that is passed to me from some caller, and I don't have information about that, so I don't neither of them. And in this case, I cannot go from the points to set relationship to the alias relationship, but I can still say that they may alias. So moral of the story is, if you have points to information, you can go from points to information to may alias information. If you cannot have points to information, you should not give up. You can still figure out the alias relationship without knowing the points to sets. So far, so good? Is that clear to everyone? Right. Cool. So generally speaking, for incomplete programs like the one we have just seen an example of, associating variables with allocation sites is either unsound or imprecise, because you don't get the accurate points to an information. So in this case, alias analysis is better suited to reason about the relationship between those variables without actually caring too much about the objects that they may point to. So this is just to summarize what we've discussed so far. We are almost halfway through the class, so let's just take a few minutes break and let's continue again at 1:15 p.m. Edmonton time. Meanwhile, if you have any questions, just ask me on the Zoom chat or the Zoom voice chat as well. I'll be happy to answer them, but we're going to continue in a couple of minutes. All right. Welcome back, everyone. Let's continue with our lecture after that short break. So before the break, we were talking about may alias analyses and must alias analyses, and when an alias analysis may be more useful than a points to analysis, specifically when we have incomplete programs. So another point that I would like to talk about is direct alias analysis. So what do I mean by that is the following. So let's say we have two statements, B equals A, C equals B. You may have may alias BA and may alias BA and may alias CB are both true. And what about if we have A equals null before then? So this probably goes back to the question that Muhaymin asked a few minutes ago. So what if we assign A to be null up there? Would we still have may alias B and A is true and may alias C and B is true? What do you think? What do you think we should do here? Okay. Okay. So, generally speaking, the general, again, one of those kind of common rule of thumb kind of thing is that if you say may alias v1 and v2 or b and a here, you really mean they may alias or both are null. So the both are null kind of part of it is usually ignored. We really mean that they do may alias. There exists some actual concrete allocation site where both variables may point to that allocation site at one path in the program. So there exists a path where both A and B may point to that allocation site along this path. So the both are null is usually ignored, and I say usually because, like I said, in some cases you may need to have that. Maybe, for example, you are tracking the null references in your code and you want to know where exactly those null references may go to because you want to check for null pointer exception. So you need to make sure that those null pointers are properly tracked in your program. So you may want your may alias analysis to return a different result here and also still respect that both variables may be null as well. So yes, it depends on your analysis, but generally speaking, a may alias would be a may alias or both variables are null. So now that we have seen when to use an alias analysis, okay, so sorry, before I move on, there is another question. Does it only hold true for null or any other hard-coded address as well? No, this is really for null. Any other hard-coded address, I mean, it would be a pointer, which means it would be some allocation site in memory, which would mean that it is not null. So if it is something other than null, because null doesn't point to any specific allocation site in memory or any address in memory. So if you're pointing, if that variable may point to some address in memory, we're just going to assume this is going to be some allocation site. So this only holds for null. I hope that answers your question, Ivan. Alright, I'm gonna assume that it did answer your question since I don't see any. Okay, alright, sure. Sorry, it is kind of hard to know the the response to things when things are done virtually, because I can't see anyone in the class as before, so bear with me with that. So now that we have seen how we can when to use an alias analysis, when can we then use a points to analysis? We have seen some examples of that when we talked about call graphs. So here's another example. So we are creating a linked list. We're calling l.clear. The first statement, we're going to call that A1, the allocation side. So the points to set of L is going to be A1. So the type of the points to set is going to be the set of linked lists. L.clear can only invoke one method, may only dispatch to one method, which is linked list.clear. So that means that we can use that for method devirtualization. So if you are an optimizing compiler, you can actually use that information from points to sets to sort of replace that virtual method invoke l.clear that you will see in the bytecode, in the Java bytecode, with a direct call to that method, which will save a lot of time for trying to resolve things at runtime. You already know exactly which method this is going to resolve to. So you need that points to information. So for call graphs, for compiler optimizations, for method devirtualization, you do need that points to information. Alias analysis here is almost useless, because what do I care if L aliases with, I don't know, some other variable V? That doesn't tell me anything really, because I don't know exactly what types the points to sets may have, what objects they may have. It doesn't help me in devirtualizing that method call or figuring out what call graphs, what edges in the call graph may be outgoing from that call site. Another concept that is related to both points to sets and aliasing is weak updates versus strong updates. So what do I mean by that? So weak updates, you're able to do them if you only have may alias information. So if you don't have must alias, but you have may alias, you can do weak updates. And it basically means that we are going to retain the previous information and add to it the new information. So we are not going to forget the old information. We're just going to keep racking up information as we go. So think of it as, again, one of those subset relationships. So the constraints that are induced in the case of weak updates are subset relationships. So you cannot kill old information, otherwise it will lead to unsound results. I'm going to introduce that concept kill here more formally and more concretely as well when we start talking about inter-procedure analysis on IFDS over the next few lectures. So for example, weak updates is a useful thing to do if you're doing constant propagation. In this case here, we're doing a constant propagation analysis, so we're trying to do weak updates during that analysis. Assume that variables are going to be initialized to 0 at the beginning of the program. So the initial values that you're assigning to your data flow analysis in the monotone framework is 0. And only may alias xy is known. So if you have x.f is equal to 3, excuse me, before that statement, x.f will have the value 0, y.f will also have the value 0 in our data flow analysis. After the statement, x.f will have the value 3, y.f will also have the value 3, because we know that may alias xy is known. However, since we must retain the old value of y.f, then we are going to also say, well, y.f may also be 0, because this relationship between x and y is a may alias relationship, so we must have both relationships. So at the end of the analysis, at the end of our constant propagation analysis, we're going to say x.f is going to be 3, y.f is going to be either 0 or 3. Because we can only do weak updates because we have a may alias information. So may alias, you must retain old values, you're going to get more results just to maintain soundness or correctness for your analysis. On the other hand, for the same example, if we had known that, or had we known that x and y must alias, with the same example, we're going to do the same thing. We're going to do something different, sorry. Before the statement x.f and y.f are still zeros, after the statement x.f is 3, y.f is 3, But since we have a must alias information, we are going to kill the old value of y.f. So that means that this y.f is going to go away, and at the end of our program, we're only going to be left with x.f is going to be 3, y.f is going to be 3. So again, must alias relationship means your analysis should be flow sensitive. It means that you potentially have the ability to do strong updates, which means you can kill old information or stale information, which means you get more precise results. So obviously must alias information or must information is more rich, allows you to do more, but it's also harder to compute and harder to prove. So the analysis might not be as scalable as you would like it to be, or might not be as precise as you would like it to be. So far so good. Any questions about weak updates versus strong updates? All right, thumbs up. So the next topic that I would like to discuss with you here is called access paths. And this is going to be the last topic that, the last topic, but we're going to have a few brief examples at the very end of the lecture. But this is going to be the last topic that I'm going to discuss with you today regarding pointer analysis. So what are really access paths? So access paths are a sequence of field accesses that start with a local variable. So you have a local variable v, and then you have a successive accesses of fields. So you keep reading a field, and from that field it's an object. It might have another field g, it might have another field h, and so on and so forth. So it's as if you are probing deeper into the object that you have a reference for, which is v. This is what an access path is. So it starts with a local variable, followed by a sequence of 0 or more field accesses. So in program analysis or static analysis, we typically use access paths as a descriptor for the objects that we may have in our program. So it's again one of those abstractions that we just use to, or labels you may call them, that we use to indicate what are the objects that we're dealing with in our program. So let's say we have a program here, x equals new x, a.f is equals x, bg is equal to a.f, c.h is equal to b. So after the first statement, we have one access path, just x. So I'm going to show the set of access paths, x. After the second statement, we're going to have two access paths, x and a.f. After the third statement, we're going to have three access paths, x, a.f, and b.g. And after the fourth statement, we're going to have four access paths, x, a.f, b.g from before, and then we're going to have c.h.g, right? Because we are assigning c.h is equal to b, and we already have b.g, so we're going to have c.h.g. So we're going to have four access paths there. So what does it mean really that we have this access path x and we have this access path xy? So what this really means is here we have only one access path and there is one object and x points to it. Here on that access path here, and when we have x and y in the same set, when we use access path as descriptor, that notation means there is also an object, might be the same as that one, where both x and y point to it. So here we have O1, here we have O2. These two might be equal to each other, but they don't have to be. So we have one object that only x points to. We have an object, possibly the same, but could be different, that both x and y points to. And every set that we're going to show would represent a unique possible runtime object, a potential runtime object, I should say. So basically every set that you see in front of you represents one runtime object, and the elements inside that set represents all the access paths that alias each other, that that represent that object, or that can be used interchangeably to represent that object in the program. And this is where you can sort of extract or deduce alias information from those access paths. So let's have an example here to understand what actually is going on. So how can we encode alias information as access paths from this example? So in this example, we have a bunch of new statements for allocation sites. Then we have an if statement, and the body of the if assigns x to y. Outside the if statement, we have z equals x, and we're going to follow through with the descriptors that we're going to have here. So after those allocation sites, we have three descriptors, x, y, and z. So we have an object that only x can point to, which is this object here. We have an object that only y can point to, which is that object here. We have an object that only z can point to, which is that object there. So what about at this statement? So at this statement, nothing has changed. We still have the same three field descriptors. And why is that point here different than this point? Well, this point is because of that arrow, but remember that we have two arrows here, so we have to merge the information from both arrows or from both paths in our program, just like we did with the merge operator in the monotone framework. We're still following the same notation, the same theory, lattice theory, monotone framework. We're still following all the notations that we have used in the previous 3 or 4 lectures or so as we're going. So here we have to merge the facts from that path and this path, that we're going to get x, y, and z right before the if statement. After the if statement, assuming that we're taking the true branch, because of this assignment, that assignment means that x is going to be assigned to y, so whatever object that x may point to, y should also point to. So what do I mean by that? Well, I'm going to see here I have x, y, and z. Now y is going to point to whatever x points to, so whenever I have an x, I should add y to that set. So this is exactly what I did here. Z will remain the same because nothing has affected z so far. On the other hand, right before that statement, if I'm merging those two facts, so what do I mean by merging here? My merge operator is going to be the union operator, just because I have one path that has x, y as a set, z as a set, and on the other hand I have x, y, and z each in their own set. So this union, so this here, so on this path, let me write that down. So on this path we have these sets of access path. On this path we have these. When I do the union, the merging, I'm going to union that with that. I'm going to get the sets x, the set y, the set z, the set x, comma y. So I have 4 descriptors. Each one represents some object, some runtime object, where only x can point to one of them, only y can point to one of them, only z can point to one of them, and there exists an object where both x and y may point to. So after that statement, z equals x, that basically means the following again. It means that whenever x shows up in any of those sets, z should also show up. Z should be added to that set. So given that these are my input facts, my v in, right, to my data flow analysis that I'm doing, what should be my v out? What should be the output here? I'll give you a minute to think about it. So if my input sets are the set x, the set y, the set z, the set xy, based on that assignment statement, z equals x, what should be my out set? Alright, so the outset should be the set y, the set xz, the set xy. Why is that? X, Z, Y, X, Y, Z. Again, why is that? If you're gonna give an answer, you should tell me why. You should give me a reason why this is the case. So what is happening here to my input set? So let's have a look here. So my input set is the set x, the set y, the set z, the set xy, and I have an assignment statement z equals x. So what that means is I'm gonna assign x to z. So if what does that mean? That means that if x is pointing to a variable in the program, z after this statement should also point to the same variable, right? So I'm going to look here, I'm going to see an x, so that means that this object is an object that x points to. So based on that assignment statement, I should add z to that as well. The second object is y, so I'm going to leave that as is. The third object is z. Well, z no longer there is no longer an object where only z may point to, because that has been overwritten by this assignment statement, so that cannot exist anymore. Or if you may, you can also say, well, z is going to point to the same object as x, but this set is the same as that one, so you can just remove it. And then we have an object where x and y may point to, and this statement says whatever object x may point to, z will also point to. So in this case, I'm going to have x, y, z here. Excuse me. So in that case, the v out of this, or the output fact here, is going to be x, z, y, and x, y, z. There exists an object where both x, z point to. There exists an object where only y points to. There exists an object where x, y, and z point to. Does that make sense to everyone? Any questions so far? All right. So we can actually, from that information that we have just seen, just by looking at the descriptors here, we can figure out may alias and also must alias. So may alias would be if there exists a set where only one set, I only need one set, where both x and y point, where both x and y are in. Must alias is if for every set that contains x, it also contains y. So they always coexist each other. So here they coexist. For all coexist. Here there exists one set where they coexist. That's enough. So may alias xy. So here, if I have xz and xyz, does x and y may alias? Well, yes, because there exists one set where they coexist, both of them. So this is going to be a true. Must alias xz, is that true or not? Well, let's see. Must alias. So there exists if each set that contains x also contains y. Each set that contains x also contains that. Each set that contains x also contains that. So this is also going to be true. What about must alias xy? Is that true or not? Based on those definitions here. false because it is not in x and z. Exactly, because there exists xz where x exists but y does not exist. So I cannot say must alias xy, but I can say may alias xy. So far so good. Last thing that I'm going to talk about is doing strong updates with access paths, how that using access path as object descriptors may enable us to do so. So looking at the same example again, looking at the same flow that we're doing here, we can actually apply strong update as follows. So before the statement here, z equals x, we have x, y, and z and xy. After the statement, we're going to assign x to all, we're going to add z to all the sets where x exists. And then we're going to have x.f equals 3. At that point, we say also that xz is a set, y is a set, x, y, z is a set. Which means that if I have x.f is 0, y.f is 0, z.f is 0, xy.f is 0. So this is going to be my initialization. So I'm again going back to the constant propagation example, and all variables are initialized to 0. After that statement, after z equals x, I'm going to do that. So I have xz.f is pointing to 0, which means x.f, which means there exists an object that both x and z may point to, and I have a dereference, a field dereference on that object, and this dereference will be assigned the value 0. y.f is assigned 0, xyz.f is assigned 0. After that statement, x.f is 3, here I can actually do a strong update, because I can look at any of the variables that x has, and whenever x exists, z also exists. So I can overwrite the value without having any problem, because I know that any runtime object that x points to, z also points to. So I'm able to apply strong update in this case, because I know that x and z must alias. There does not exist a runtime object where x and z don't point to at any point in the program. So that allows me to do strong updates. So one last thing before we finish our lecture today, just a quick word about pointer analysis and distributivity, because this is going to come back again later in the course when we talk about IFDS, or the inter-procedural finite distributive analysis problems. We have a few statements here, x equals a equals b, and then we have a merge point, x.n equals y. On one side, we have the field descriptor xa, which means a runtime object where both x and a point to. On the other hand, we have the descriptor ab, which means an access path where both ab point to. And here we're going to say, well, I'm going to merge both such that, by merge I mean again union. So I'm going to get the set xab, which is not going to be precise, admittedly, because I am just grabbing in all the points to information from both branches, if branch, an else branch, or a true branch and a false branch. And admittedly, this might be imprecise, but this is going to be a distributive flow function if I define it as such. And we're going to talk about how that actually helps in making our analysis run in a more reusable fashion, as we're going to talk about when we come to IFDS. But generally speaking, pointer analysis is not a distributive analysis. In the general sense, pointer analysis is not distributive, meaning you cannot define flow functions that are distributive that compute pointer information. And the reason for that is that when you merge first, you're going to get different results than merging later. Generally speaking, applying the function on the merge of x and y, two items in the lattice, is not going to yield the same result as applying the function on each element separately, then finding the merge in the lattice. We're going to get to that also further along in the lecture when we come to IFDS. So just a quick recap of our lecture today. We talked about certain points to analyses that can be used to answer also alias queries. The advantage here is that you can just have one analysis, the points to analysis, and you can reuse its result to find out more information about aliases and so on. Rule of thumb, must alias information means you need to have a flow sensitive setting, otherwise your analysis is going to compute garbage results. Strong updates consequently needs or requires must alias information, which means it also requires flow sensitivity or a flow sensitive analysis. In general, a flow sensitive points to analysis is not distributive, but there are some workarounds that we're going to see later in the course that would enable us to do or to define the analysis as such. That's it for today, folks. And on Thursday, we're going to start going beyond the boundaries of one method and start to define an analysis that is inter-procedural, crossing method boundaries. Now that we can do analyses intra-procedurally using the monotone framework and lattice theory, and we understand now how we can cross the method boundary through call graph construction and pointer analysis and alias analysis, we're going to merge these two together to obtain an inter-procedural analysis that can run throughout the whole program, and we're going to see that in our lecture on Thursday. That's it for today, everyone. Thank you all. We still have a sort of a minute or two for questions if you have any. Otherwise, thank you very much for today.